Hi students, in this video we are going to derive the relationship between focal length and radius of curvature. So focal length and radius of curvature. So what is the relation between F and R? So basically since we already know this, or assuming this we already know, I am going to write F is equal to R by 2 or R is equal to 2 times F. So this particular thing we are going to derive in this today's video. Okay, so just to save the time, I have already written everything with the ray diagram even. So here if I consider concave mirror, here I am considering convex. For any kind of mirrors, for any kind of this, both the figures can be written for the derivation purpose. So you can write any one in your examination. Okay, now if we consider concave mirror, so here we have C, it is center of curvature. Here we have F, principal focus. So this is pole. Okay, this is the midpoint of the aperture. Okay, now the ray is coming like this and striking this particular point M. This is reflecting back in this particular, and it is passing through the focus, right? And we already know that, so we should write the normal for this particular thing. Okay, so for here, if this is anyway curved surface, but at this particular point we can draw a normal, straight line, because this is a straight line. For this particular line, this is 90 degree. Okay, that's why it is actually from center of curvature to any point on the curved surface will form a normal. So this is angle theta and this is also angle I, theta. It means this is I and this is R, but since I is equal to R, so we are simply writing theta for our convenience here. So this is theta, here also this is theta. Okay, now here we have theta, here also we have theta, but how this comes? This is theta and how this is 2 theta. Yes, so here we have two parallel lines, right? And this is the bisector, right? This is a bisector for this particular two lines. Here also we have, this is bisector for this two lines. Okay, so here if this is theta and this must also should be theta. Okay, because the alternative angles. Okay, now this is theta because angle of incidence should be equal to angle of reflection, so that's why this is theta. So if this and this is theta, obviously this will be 2 theta because the exterior angle. Okay, so if we consider this triangle, the sum of two angles will be equal to the exterior angle. Or else if we take one more, like this ray and this ray are parallel, obviously this will be the bisector. So here total angle, this is 2 theta, hence this is also 2 theta. So similarly in this case also we can construct the same thing. So theta, this is 2 theta, this is theta and all. So all these things whatever I have explained here, this can be applicable here also. Now straight away we'll come to the mathematical part of this derivation. So now let theta be the angle of incidence. So already told you theta is the angle of incidence. Then even the theta, this theta is also angle of reflection we can call, because I is equal to R, so theta is equal to theta here, right? So from the figure, triangle MCP is equal to theta and MFP is equal to 2 theta. So why we are actually concentrating on triangle MCP and MFP? Basically we have only two triangles in this figure. One is MCP and MFP. So here we have D actually. So the distance between D and P is negligible. So in coming steps we are going to take this. Okay. So sorry, I have written MCP here. So if we neglect this D and P, okay, since this is actually a microscopic phenomena, but here in the figure it is macroscopic. So if we consider parallel rays like this, these are very near parallel rays. These two parallel rays are very, actually it is like this. Okay, this parallel ray is coming like this. Okay, and this is falling like this. Okay, so this theta will be very small, and this actually looks very straight line, right? So see here also this is curved, but this is straight line, but in actual sense this is almost very narrow in size, so that's we are going to consider the straight line. Okay, so here this MD is nothing but MP, we can replace it. That's why in this figure tan theta, okay, so why we are taking tan theta basically? So from this figure, MCP angle MCP is equal to theta and MFP is equal to 2 theta we have taken, because this is 2 theta, this is theta. But now for this theta, this is opposite and this is adjacent. So in the trigonometric functions, we have in which particular function we have opposite and adjacent, that is tan theta. So that's why we have taken tan theta here and tan 2 theta here. Okay, so basically in the figure, in the triangle MCP, if we consider tan theta, then tan theta is equal to opposite by adjacent, that is MD divided by CD. Okay, MD divided by CD. Now if we consider, so here also it is same, theta is equal to here if I write MD divided by CD. So we have written the same thing, so this is applicable here also. Anyway, we are going to focus at this particular figure. Now tan 2 theta is equal to, see here, tan 2 theta is equal to MD divided by FD. So we have MD divided by FD. Now already told you, if the rays are paraxial rays and it is very closer to the principal axis, so this ray is parallel, so then theta will be very small. So for very small angle or very small theta, so tan theta is approximately equal to theta, and tan 2 theta is equal to approximately equal to 2 theta. So you can actually put some value here, very small value. So tan whatever the value, very small value, will be equal to again the same value. That's why tan theta is equal to tan theta. Here also the same thing. Now if I take tan theta is equal to theta and substitute it here in the equation number 1, and tan 2 theta is equal to just 2 theta in this equation number 2, so equation 1 and 2 will become like this. Okay, so see here, instead of tan theta I have only theta here, then MD by CD is the same thing. Here also I have, instead of tan 2 theta we have only 2 theta, so again MD by FD is same. Okay, fine. So now I'll send this to this side, so this is theta is equal to MD by 2FD, right? So now equation, comparing equation number 3 and 4, we can write like this, because because theta and theta LHS side equal, that's why RHS side should be equal. Now MD get cancels, so we can write this FD is going to send, I'm going to send this here, FD divided by CD is equal to half. Now that's why FD is equal to C by 2. Now for very small theta, okay, if theta is very small, this theta is very small, it means this particular line. Okay, now if I keep on decreasing the size, this point will be very near to this point. Okay, if this is near, if suppose M is here, so this line here, so D and P are very close, right? That's why I'm telling here, if theta is small, point D is very close to point P. So we can make a conclusion that therefore FT is approximately equal to FP. See here, FD, if it is very close, then FP and FD is nothing but same. Similarly, CD is nothing but CP. So I have taken the same thing here. Okay, FD is equal to FP is equal to F, small f, that is focal length, and CD is equal to CP is equal to R, that is radius of curvature. So if you substitute 6 and 7 in equation number 5, we get this finally. F is equal to R by 2, or R is equal to 2 times F. So this is the relation between focal length and radius of curvature. Hope you got this derivation clear. Okay, thank you very much.